So now we are going to discuss work as potential and kinetic energy. As we have just discussed that what is work? Work is actually the dot product of force and displacement, which we put it as Fs cos theta. Now this work is nothing but is getting converted to potential and kinetic energy. Well, how we do so? Let's consider potential energy first. Now, say for example, I have a body here which is acted upon by a wet mg, and I want to lift it to somewhere there at a height h above the point. So the work here should be force into displacement, and displacement is h, and the work and the force is nothing but the weight of the body. So you see, the work becomes mgh, which is nothing but the expression for potential energy. So that's a very easy way to show that how work gets converted to potential energy. Now, in the same way, you have to understand the calculus notation of the whole thing. And in the calculus notation, you must have been careful that when we write potential energy, I will start with force rather. We write the force as minus du by dx. So there is a force, and then du, we put it as minus f dx, which implies that this work has to be done against the field to store it as potential energy. So this minus implies that the work is done against the field. Now that is again a very important point, that the work has to be performed against the field for it to get it stored as potential energy. Now again the example of the wet, as I'm putting the wet up there to a height h, what I'm doing is I'm working against gravity to put it up. So that is why this work gets converted to potential energy. Now I will discuss the form of kinetic energy as work. Now again, if I begin with work, as you all know is force times displacement, and the force by definition is mass times acceleration. Now all of us have come across this equation of v square is 2as for in kinematics. So a particle possessing a velocity v having acceleration a and travel for distance s. Now as can be put as half v square in that case. So if I replace this value of s in our expression for work, then it comes to m into half v square. So that is nothing, half v squares. That is nothing but the kinetic energy half mv square. So again we can show that work, which is force times displacement, lands up to half mv square. So this is how we can treat work as potential and kinetic energy, remembering very well that the potential energy form is only applicable for conservative forces, while both kinetic and potential for non-conservative forces. The same theory is applicable for a spring as well, the potential energy part of a spring. As you have a spring here, and as you know, the force that you have applied on it is getting converted to the force which we call the Hooke's force. So F, as you all know, can be put as minus kx, where kx is the restoring force. When we take the magnitude of the force, we consider it as simply kx. Now here the potential energy part of the spring comes from the work itself again. So that work, as we can calculate here, is the average force. Now the point remains that why we consider the average force here. The average force is due to the fact that when the spring is in its natural length, the force here is 0, and when you elongate it to a particular point, the force becomes F. So this gradual increase from 0 to F makes the force average. So this work is 0 plus F by 2. Now where comes this 0? The 0 is the force where the situation is at its initial natural length position, and then when you extend it, it comes down to an extension of x, and the force is F. So that into x. So if I put it like this, then I will come to the next portion as something like this, that the work done here is half into F into X, because the displacement is X. And we can put it as Kx, the force. So that is very important now. This work is what is the stored potential energy of spring. So the stored potential energy of spring is half K x squared. So as you can see, in every mode, we have the potential energy getting converted to work getting converted to kinetic energy, and so on. That's all for now. Thank you. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.